Hello students, we are going to start the second lecture on this chapter, Mechanical Properties of Fluids. We have already covered 3 pages of your textbook of this chapter. Our next topic is atmospheric pressure. The topic is quite simple. What is atmospheric pressure? Atmospheric pressure is nothing but the pressure of atmosphere over a particular point. Now, when we consider atmospheric pressure, we have to consider the force. Now, this force is due to the air present over us. Okay, let us consider here we have a sea level like this. This is your sea level, and we want to find pressure over here. Now, to find pressure over here, we have to consider the layers of the air present above it. I hope you understand. The layers of the air present above it. Now, layers of the air till what height? We have already studied that in Earth's atmosphere. We have troposphere, we have stratosphere, we have mesosphere, we have ionosphere, which extends till 400 kilometers. So are we supposed to consider the air weight till 400 kilometers? No. We have studied that density of air goes on decreasing as we move towards the height. So after 8 kilometers of height from the sea level, the density of air is almost considered as negligible. So we are supposed to consider the weight of the air till what height? Only 8 kilometers. Okay. And then the weight of the air, that is the force, divided by the area, that will give you the pressure. Now this pressure, which will be termed as atmospheric pressure, comes around 1 bar. 1 bar is also termed as 1 atmosphere, and perfect value of this 1 atmosphere is 1.013 into 10 raised to 5 Pascal. I request you to learn this value because it's not expected that it will be given in exam and in numerical, and this is a standard value which you should learn. Okay. After this, our next topic is absolute pressure and gauge pressure. Okay. Now consider a case if I'm asking you to find pressure somewhere here below the water surface. Let us consider the height of this is 200 meters. Okay. Now if I want to find pressure at this point, we have to consider 2 pressures. First of all, pressure due to this 200 meter of liquid column. Okay. Plus the pressure due to this atmosphere. So ultimately at this point we are finding total pressure, and that is what is called as absolute pressure. Okay. So if I write absolute pressure, P absolute, this will be equal to P atmosphere plus this much rho Hg. Okay. This is what is called as absolute pressure. Now what is gauge pressure? Let me tell you this much term. Rho Hg will be termed as gauge pressure. The definition of gauge pressure is very simple. It is nothing but difference between absolute pressure and atmospheric pressure. So if I subtract this two, P absolute minus P atmosphere, that will be giving me rho Hg. Correct? And this is what is your gauge pressure. So I can write P absolute minus P atmosphere is equal to gauge pressure. So these are few terms related to pressure. You can note it. After this, we are going to take one numerical from your textbook unsolved part, numerical number 10. Okay, so I am reading the question. It is find pressure 200 meter below the surface of the ocean. So the diagram is drawn 200 meter below. At this point, you are supposed to find the pressure. Okay, and the pressure on the free surface of liquid is 1 atmosphere. Means this is the free surface of the liquid which is open to the atmosphere. At this, the pressure is equal to 1 atmosphere, and we know it is nothing but atmospheric pressure. So in given, I will be writing, we are given the height h is equal to 200 meters. Okay, we are given the value of P atmosphere which is equal to 1 atmospheric. Okay, and as well we are given in bracket the density of sea water, ocean. So density is equal to 1060 kilogram per meter cube. Usually density of fresh water is to be taken as 1000. Okay, and for sea water it is bit higher. We are supposed to find the pressure. Now the question arises, are we finding absolute pressure or are we finding gauge pressure? So you know at this point two pressures are to be considered. First due to this 200 meter and second atmosphere. So we are actually finding total pressure which is equal to absolute. Okay, so here is our solution. The formula is seen at atmospheric plus rho h. Atmospheric, just now I had written the value of atmospheric pressure which you should be aware, which is 1.013 into 10 raised to 5 plus density 1060 into height value is 200 into g value is to be taken as 9.8. This term you can directly multiply. So let's see what answer will come for this. When you multiply this, you get an answer which is equal to 2077600. Okay, direct multiplication. And now the question arises, we cannot add this 2. The reason being, here power is there, here power is not there. So we will have to convert this into 10 raised to 5. So shift this decimal at the end 5 digits. Okay, 1, 2, 3, 4, 5. So our next step will be okay. Now 10 raised to 5 can be taken as common. Now you can simply add this to, okay. So this will give you 21.789. So your last answer is 21.789 into 10 raised to 5 Pascal. So this is what is your final answer to this numerical. Okay, please you can note it. Okay, so now our next derivation is this P2 equal to P1 plus rho x1 minus x2 into G. Here the diagram is, there is a vessel. Inside that vessel we have a cylinder kept. Okay, and let me define you the terms. The height from the bottom of this vessel till this point is termed as x2. From this bottom till this top point of the cylinder is termed as x1. This is our x1. So when you subtract x1 minus x2, I hope you can understand, you will get this height of the cylinder which is our h. So I can very well write x1 minus x2 is nothing but equal to h. Okay, then what are pressure 1, what are pressure 2? Just try to understand that above this top part of the cylinder there are some layers of liquid. So the weight of this liquid layer will act like a force. Okay, so here we have force F1. Okay, then we have to consider force F2. Just understand a concept of buoyant force. You must have heard this buoyant force. Take a plastic bottle, empty plastic bottle, and try to dip it in a container filled with water and try to push it very hard. Okay, Then when you release that bottle, what is your observation? That bottle will come up. Okay, it is empty bottle. Obviously, it is packed with the lid of the bottle. Correct. So the bottle is coming up. The reason is there is definitely some force inside the liquid which is acting in upward direction. So that is the force which we are going to draw in upward direction here, which will be denoted as F2. Okay. Then inside this liquid also, inside this cylinder also, we have liquid filled. Okay. So the weight of this liquid inside the cylinder also has to be shown. So that weight will be shown exactly at the center of the cylinder. So let us consider this is that weight which I will be writing as mg. So this is a diagram, okay, which I have completed. Now let's try to understand. Since these all things are in equilibrium, we know that upward forces are balanced by downward forces. So here, upward forces, I can see it is only F2. Okay, so I'll write F2, which is balanced by downward forces, which I can see it is F1 plus mg. Correct? Now we know the formula for pressure. Pressure is equal to force divided by area. So therefore, force formula can be written as pressure into area. So if I write F2, then it will be P2 into A. And if I write F1, it will be equal to P1 into A. Substitute these values over here. So therefore, I will get P2A is equal to P1A plus M into G. Now, consider our previous lecture. Mass can be written as density into volume. So density into volume into G. Again, volume can be written as area into height. So I'll write this as area into height into G. Now you can observe A can be taken as common. So P2A is equal to A is taken as common. P1 plus rho into H into G. A gets cancelled. So we are left with P2 is equal to P1 plus rho HG. Correct? Now instead of H, I can always substitute x1 minus x2. So our last part will be P2 is equal to P1 plus rho x1 minus x2 into G. I hope this matches. Okay, so now let's use this formula in two different cases. In first case, you can see the cylinder is just touching the surface of the liquid. Okay, so let's try to find out what is P1, what is P2 in this case. Okay, so this point will be your x1, this distance will be your x1, then here this distance will be your x2. When you subtract x1 and x2, that is obviously going to give you h. This will be your h. We want to find pressure at this point. So this pressure will be termed as P2. Okay, and here at the top, the pressure will be termed as P1. Okay, so you got all the terms. And let me tell you about this point. We have nothing but atmosphere. So P1 can also be written as P atmosphere. So if I want to find P2, what I'll have to consider? Simple. The pressure due to this liquid column in the cylinder plus pressure due to this atmosphere. So instead of P1, I'll be writing P atmosphere plus rho x1 minus x2 is nothing but height, that is h and g. So this becomes our formula. Now it's not that difficult. In simple words, if I had asked you a person is standing at this point, you are supposed to find total pressure, then I think you would have done the same thing on simple logic. The same formula we have just derived with the help of a new terms. Okay, so it's not that difficult. Let's go on to the second case. Here, the difference is cylinder is outside the free surface. Okay, it is bit outside. So in this case, let us consider this as the, instead of H, I am denoting it as D. Here, the pressure will be termed as P1. Now, why? Because on a particular level, the pressure remains same. You know that. Okay? Whatever pressure you get over here, the same pressure you will get over here, the same pressure you will get over here. And we are interested in finding pressure at this point, the top. So wherever we want to find pressure, that will be termed as P2. Okay, and this will be termed as P1. If I ask you what is the pressure at this point, you will say this is open to the atmosphere. So this will be equal to atmospheric pressure. Okay, so P1 is nothing but equal to atmospheric pressure. Is it clear? So if I write P1 equal to, then I need to write P2, this much pressure, plus pressure due to the air present inside the cylinder. So P1 can also be written as P2 plus the air present inside the cylinder, which will be rho dg. Okay. Now we are interested in finding pressure P2. So therefore P2 will be written as P1 minus rho dg. So this becomes the formula if the cylinder is outside. Now I'll just relate this with atmospheric pressure at Mount Everest. As you go on above the sea level, this is moving away from the sea level. Okay, this was at the sea level. This is moving away from the sea level. So what is your observation? As you move towards height away from the sea level, some value has to be subtracted. If you go towards Mount Everest, definitely you are moving away from the sea level. So some value will keep on getting subtracted. And from P1 it will be getting subtracted. And P1 is nothing but my atmospheric pressure. From this, rho dg is getting continuously subtracted. So final value after subtraction, whatever you get is definitely going to be less. And hence, the pressure goes on decreasing as we move away from the sea level. Okay, so you can have a look at this. Okay, so we are moving on to the next topic, which is hydrostatic paradox. Paradox means contradiction. Contradiction is something which we expect and something opposite to that is coming out. Okay, so let us understand what is hydrostatic paradox. I've written the shape of the vessel containing the liquid does not affect the pressure. I'll just give you a simple example. We have three vessels having different shape. You can observe different shape, different amount of liquid also, let me tell you. Okay, and if I ask you, we need to find pressure at A, pressure at B, pressure at C. Which one will be greater? Then most of you will think more liquid. So obviously more pressure at point C. So this is what is paradox. Let me tell you, pressure at A will come equal to pressure at B will come equal to pressure at C. So this is what is written over here. Shape doesn't matter. Okay, shape is not the requirement for determining the pressure. Pressure is dependent only upon the height of liquid. Okay, you can observe these diagrams. The height of the liquid is same. Okay, and most importantly, yes, area is also kept same. Area of all the three vessels is same. So shape doesn't determine the pressure, it only depends on height. And why is it so? Because we know the formula for pressure, rho hg. So it depends upon density, it depends upon height and gravity. acceleration due to gravity. So if height is kept constant in all the three vessels, irrespective of the shape, the pressure is going to remain constant. I forgot to tell you, this three vessels have same liquid, so the density is also same. So this is about hydrostatic paradox, and we complete today's lecture number 2. Thank you.